So we're going to continue our introduction to physics. If anything, we could maybe call this unit or chapter or unit 0.5, maybe with that, because it's there. It is still in chapter 0. It is a little bit of switching the gears. I did want to kind of add a little bit of change into it so that we're not making the test too large. I think at the beginning I thought it worked out really well for both A and B day students to take it, and you're done before the hour got done. I don't think that has ever happened on that first test in physics, which is quite an anomaly. So, way to go. So, we kind of did a little bit of this, and with talking about the motion diagrams versus a dot diagram, or the particle diagram, and we're going to get into looking at, and more specifically this over the next couple days, is more of the coordinate system. Okay, and that will force us to need to use our X and Y coordinate systems that we remember more from a math class. Okay, some of you, I have always heard in previous years of physics, it's just like a math class. It's just like a review of pre-calculus, or which would be very similar to like a college algebra. It's very similar to that. You're right, there are some things. We will, as we introduce the vector components and some of these other coordinate systems, we're going to we're going to start and kind of add things before we start adding angles to things. Okay? We move forward with the origin, that X and Y being the 0 point. As we move forward as the origin, I don't think anything beyond new to us as we move forward as well. So there are some things that we have to identify. What is a vector quantity and what is a scalar quantity? A vector quantity have both magnitude and direction. Scalar quantities only have magnitude. I give some examples of vector quantities such as displacement, velocity, and force. Those are the ones that we use a lot in here. Scalar quantities, temperature, we could even add energy to that. And that can be both kinetic or potential energy with it. Scalar quantities are like filling of a bucket. You just know you got the bucket filled. Where vector quantities are going to have a little bit more, shall we say, direction in telling us, it's not just telling us how much, but in what direction. And just like the movie Despicable Me, you have the evil vector that commits crime with both direction and magnitude. Oh yeah. So, as many of you know, most coordinate systems require the X and Y axes. Some of you may or may not remember them. Hopefully you do. But just as a reminder, X is there. The Y axis makes the Y. Once you find out your y-axis, usually it's pretty self-explanatory. And those of you that care, there is the z-axis. Or if you're Canadian, the z-axis. We're not going to deal with those. Well, we might, but it'll be algebraically solvable. Usually we're only going to, and that's where we get into. We're going to talk about how do we solve vectors. We're going to deal with vectors in one dimension at one time. Okay, we're going to talk about triangle-based ones, and that's two-dimensional stuff. But when we start out, and especially in chapter 1 or unit 1, it's going to be motion in one dimension. So it's going to go left or right or up or down, not both at the same time. When we get into motion in 2 dimensions, or chapter 2, then it's motion in 2D, then it's going to be moving both left and right and up and down at the same time. And that's what allows for some of that. Being able to graph is an important part of being able to solve our vectors quantities, because ultimately that's what you're doing. Also, being able to look at a graph and figuring out what's going on with the motion. What is that graph telling you? And that's why the graphing lab is there. And that adds some added importance, understanding of our coordinate systems and some of those types of things. A lot of time we're going to be dealing with time-based stuff. Sometimes there'll be other things. And so the time is going to usually be on your x-axis. Now becomes the other philosophical debate, can time ever be negative? Ultimately, kind of no, and then that tells you you kind of have to do some things a little differently, or something went wrong somewhere. There will be times where a distance or displacement, better term, can be negative. And especially if we're looking at things like on more of a number line when we're visualizing our numbers. An object can start at a negative value and then move positive. The 0 point then, or the origin then, becomes a different indicator. That is where the detector is at. That doesn't mean that that is where the object is at. And in some cases, as we move forward in the lab, it's important for us to have our object behind the detector to get itself up to a constant speed and or velocity, and not, because we don't want to see the acceleration part of it. We're worried about a constant velocity, and what does that look like graphically? Well, if we have it other ways, it's going to have that acceleration, then it's not going to have that constant velocity. So where, and that would be then, you're ultimately, the object is starting behind the detector, and that's where you would have that. In some cases, they'll have it even a little bit differently. They say diagrams are useful in making these estimations. It is imperative that you draw out. It doesn't have to be great art. Okay? As you have seen over the years, for some of you, I do not have great art. Okay? That is not where my talents lie. However, drawing it out to the best of your ability, and some of you have great ability, so then you're going to have to almost bring it down a couple notches because you can spend too much time drawing it out. But drawing it out helps. It helps gives us that visualization of what we're seeing. It helps us put that number. And sometimes you'll even have the drawing on the XY axis so you can kind of see what's happening as it moves in that coordinate system. And you can see then why an object can go negative in the Y direction. Or how an object could start at a positive X or a positive Y and go negative Y. Or start in the negative X going to the positive X. It does help those estimations. And the lab that we do, that I'm asking that you have a protractor for, if you do a good job of scaling your drawings correctly, sometimes if you're stuck and you draw it out well, you can literally measure out an approximation of the correct answer if you draw it out well. And that's what that not the graphing lab, but the vector lab has you do. Has you draw some things out, make the measurement, then do the math and see how well you scale. There is going to be some error involved, but you're going to find yourself going, oh wow, I really take my time. I can get close to what the answer should be. So then you have an idea of kind of where you're going. And I think that's happened a number of times to probably a number of students throughout the years and in the future as well. If I just need to see what the answer is and see if I'm moving in that right direction. And I think that can be very valuable to a lot of students as we kind of move forward. So when we look, and again, just to further define these quantities, scalars are scalar quantities, vectors are vector quantities. Major difference is your directional component. Both of them have magnitude. Okay? Scalar quantities, that's all they have. Like I mentioned in the previous slide, it's like filling a bucket. You just know you got a lot of it there, right? But it's not going anywhere. You just have a lot amount. Where the vector quantities have that magnitude, but it's now telling you where it's going. And a lot of times we're going to represent those vector quantities with arrows to help us visualize the direction that they're going. There will be times when the vector quantities are going to be very specific at what angle things are being launched, shot, or projected at. Or moving. But the fun one is always the launch or shot at. But moving adds it in as well. Thank goodness for Despicable Me giving us that video clip. I think that's the biggest thing for it. And just to kind of further and finish off some of the terminology part with vectors, length of a vector, should give us the magnitude. Sometimes I'll even see it that literally the size of the arrow as well. So some arrows will be nice and little. They're like, oh, look at this little arrow. And it's a nice, but it tells us how long it is, usually tells us how big the magnitude is. I've even seen them where they get into then where the arrow has a little bit more girth to kind of tell us the magnitude as well. Maybe it's not moving a lot in one direction, they just make it bigger to understand that it has a lot of magnitude with it. Usually forces give us those big arrows. The other ones tell usually little small arrows. But adding the arrows up gives us what's called the resultant. I don't believe that's too far off of math terminology as well. The resultant, the C, the whatever it is, it's the tail of the first origin to the tip of the last. That is your resultant. It might not always be nice and a triangle. For those of you that do calculus, go ahead, don't rearrange them. The rest of us that are going to use algebra are going to rearrange them to make triangles. Or at least make it so that we can see a triangle present. Because triangles are our friend, because we can use a lot of different math and algebra to solve them. Such as the law of cosine, or the law of sine if they're not right triangles. Some would call them wrong triangles, but they're not. They just don't have that nice 90-degree angle in there. If you have that nice 90-degree angle in there, then you get to use your Pythagorean theorem, your sine, cosine, tangent, so, ka, toa. If you have the law of cosine or the law of sine, then you have to use the equation sheet if you don't have those memorized. My suggestion, don't try to memorize it unless you're just like that person that's like, nope, I'm going to memorize it, and if I get it wrong, it's my fault. No, don't. I always come to the real, like, if I wasn't required to memorize the equations in my physics class, why would I make students memorize it in the ones that I teach? I'm not going to say that there isn't ones that some of you might take a physics class in college that requires you to memorize them. If you take the calculus-based physics, they just make you derive all of your equations. They give you one and they say, find the rest out yourself. So they does have a little bit of both.